So what is a performance testing? A performance testing is a testing practice performed to determine how a system performs in terms of responsiveness and stability under a particular workload. In other words, performance testing identifies the maximum number of users a system could support and identifies the system bottlenecks. We'll analyze later what it is a system bottleneck. As in any domain, in any activity, we have an ubiquitous language for performance testing. This is a common set of words and keywords used to communicate in a team, in a performance testing team. Ubiquitous language is a shared language used by all team members involved in a project, including developers, business experts, and stakeholders. So this is a diagram of a performance testing ubiquitous language. So end users, technical experts, and domain experts are using the same language in order to communicate during a performance testing activity. In other words, when creating a ubiquitous language for performance testing in a development project, it's crucial to define terms and concepts clearly so that all team members, regardless of their role, can understand and communicate effectively. This is a list of common words used in performance testing. So we have a latency, throughput, concurrency, benchmarking, for performance metrics, resource utilization, bottleneck, error rate, capacity planning, and root cause. What is latency? So latency, we could have, for example, a software latency, a hardware latency, and a network latency. So for hardware latency, it is the time taken for a system to respond to a request. The purpose is to measure how quickly a system processes and responds to inputs. An example would be measuring the time between sending a request to a server and receiving a response. This is a hardware latency or a network or environment latency. But we could have a network latency. For example, you're generating requests to a test server, and your computer is located in one place, and the test server is located, for example, far enough, and it is the network latency. It is the time taken for a request to reach the computer, and then the test server, and then test server sends a response, and it is the time taken for response to reach your load generator. What is a throughput? The number of throughput is the number of transactions or requests a system can handle within a specific time period. It is used to evaluate the capacity of a system to process a large number of requests. And an example would be the number of API requests processed per second. What is concurrency? So concurrency is the ability of a system to handle multiple tasks or requests simultaneously. Purpose is to ensure the system can perform well when multiple users or processes are interacting with it at the same time. For example, testing how many simultaneous user logins a web application can support. Not only user logins, but it tests how many requests, for example, how many report generation, for example, if application has a report generation or it has a listing, some kind of listing of products, how many users the application could support in order to perform well when listing a larger number of products. And it could happen that application, a software application could support multiple logins with the same user, but it could happen that the same application cannot support multiple logins with the same user. It is depending on the architecture of application. What is a benchmarking? Benchmarking is the process of comparing the performance of a system against predefined standards or competitors. The purpose is to assess relative performance and identify areas for improvement. Example would be comparing the response times of different versions of an application. What is performance metrics? Performance metrics is quantitative measures used to evaluate the performance of a system. For example, response time of request, throughput, error rates, resource utilization. Resource utilization it is meant to be, for example, monitoring of hardware, for example, CPU usage, memory usage, disk speed usage, and network. What is resource utilization? The extent to which a system uses hardware resources such as CPU, memory, disk, network, bandwidth. Our purpose is to ensure that the system uses resources efficiently and does not suffer from bottlenecks. For example, monitoring CPU and memory usage during a load test. What is error rate? Error rate is the frequency of errors occurring during performance testing. We measure error rate is used to measure system reliability and identify issues affecting performance. For example, the percentage of failed transactions during a load test. I could say here about error rate that error rate is used to determine if a test is good or not. For example, a client could say that he wants an error rate not more than 10% of requests. For example, we have a login page and we are testing the corresponding login page after a specific period of time. We identified that error rate after this test, after performing this test, an error rate would be 15%. If it is more than 10%, then the corresponding test is considered to be failed. If it is below than 10%, the performance test is considered to be passed. So error rate could be set by a client, but it could be set by a performance test engineer. And there is a standard on the market of performance testing that error rate should be not more than, for example, 5%. What is capacity planning? Capacity planning is the process of determining the required system resources to meet future demands. The purpose is to ensure that the system can handle anticipated growth without performance degradation. An example would be estimating the required number of servers based on project user growth. What is a root cause? A root cause is a term used not only in performance testing but in applications management. A root cause is the fundamental reason or underlying factor that leads to a problem or issue. Identifying the root cause is crucial in problem solving and process improvement because it addresses the issue at its source rather than just treating symptoms. And we have a very important term like a system bottleneck, and it is very often used in performance testing. A system bottleneck is a component or resource within a computer system that limits overall performance of the system. And this is an image of a system bottleneck. It shows us that, for example, we have a number of requests, but there is a component which limits processing of requests. For example, it could be a component or a hardware, or for example, a CPU or a memory, which does not allow to process a specific number of requests per second. Basically, a bottleneck means if your system wants to process 1,000 requests per second, but one of the components can only support 100 requests per second. Then Let's talk a little bit about testing type like functional and non-functional testing. Functional and non-functional testing are two broad categories of software testing. Both are critical for ensuring that a software application meets requirements and provides a good user experience. Functional testing. Functional testing focuses on verifying that the software functions according to its specified requirements. It primarily deals with what the system does. This type of testing checks the application's features, functions, and operations to ensure they work correctly as expected. So, key characteristics of a functional testing are focus areas. So the functional testing objective is to validate the behavior of the software against the functional requirements. Related to focus areas, we have following areas like user interfaces, APIs, databases, security, and client-server applications. Related to approach, we have it is usually black box testing, meaning the tester does not need to know the internal workings or code structure. Related to types, we have following types. We have unit testing, we have integration testing, we have system testing, we have user acceptance testing like UAT, smoke testing, and sanity testing. Unit testing tests is a testing individual components or functions. Integration testing, testing combined parts of an application to ensure they work together. System testing, testing the complete system as a whole. User acceptance testing, validating that the system meets the business needs and is ready for deployment. Smoke testing, a basic test to check whether the most crucial functions work. Sanity testing, quick tests to verify specific functionalities after changes or fixes. Key aspects covered by a functional testing are correct data processing and handling, proper integration with other components or systems, handling errors and exceptions, and ensuring security features like authentication and authorization work correctly. Let's analyze non-functional testing. Non-functional testing, on the other hand, focuses on how the system performs under certain conditions, rather than whether it performs the correct operations. It addresses the quality attributes of the system, such as performance, usability, reliability, and scalability. Key characteristics of non-functional testing. The objective is to evaluate the system's readiness, performance, and behavior under various conditions. Focus areas are system properties and user experience aspects that impact the overall quality of the product. Approach. We have a white box and black box, depending on the requirements. Also, we have types, non-functional testing types like performance, usability, reliability, security, compatibility, and scalability. Performance testing, assessing speed, responsiveness, and stability under load, like load testing or stress testing or soak testing. Usability testing, ensuring that the system is user-friendly and easy to use. Reliability testing, evaluating the system's ability to function under expected conditions over time. Security testing, checking for vulnerabilities and ensuring data protection. Compatibility testing, verifying that the software works across different devices, browsers, or operating systems. And scalability testing is testing how well the system scales with increased load. Key aspects covered: response times and throughput under varying conditions, resource usage like CPU, memory, network, disk under different scenarios, the system's stability and reliability over time, and accessibility and usability from the end user perspective. Differences between functional and non-functional. For example, if we analyze the focus, functional testing ensures the software works according to requirements. Non-functional testing ensures the software meets performance and quality standards. Objective. Functional testing, the objective is to verify what the system does, and non-functional testing to verify how the system performs. There are different types for both. So functional testing is unit, integration, system, UAT, smoke, etc. And non-functional testing is performance, usability, security, reliability. From the requirements perspective, functional testing is based on functional specifications or requirements, and non-functional testing is based on non-functional requirements such as performance criteria. From the testing approach perspective, we have functional testing is generally black box, and non-functional testing can be black box, white box, or gray box. The output for functional testing is pass-fail results based on functionality, and for non-functional testing, the output is measurements and analysis of performance, usability, and so on. In conclusion, both functional and non-functional testing are crucial for delivering high-quality software. Functional testing ensures that the application meets the specific requirements and performs correctly, while non-functional testing ensures that the application is efficient, reliable, secure, and provides a good user experience. Together, they provide comprehensive coverage of both what the system does and how it behaves. So there is a very famous a key term, a key concept in performance testing, like system bottleneck. In the performance testing, a system bottleneck is a component or resource within a computer system that limits the overall performance of the system. This is an image of the system bottleneck. The bottleneck could be in a component, so it could be a software bottleneck or it could be a hardware bottleneck. Basically, a bottleneck means if your system wants to process 1000 requests per second, but one of the components can only support 100 requests per second, then that component will become the bottleneck of the system because that component limits the scalability of the system. So types of the bottleneck: software and hardware. Software, when there is a component or some kind of logic that limits the overall performance of the system. Solution is to perform software optimizations like improving code's logic or adding indexes to the tables to the database during performance tuning process. Hardware and the hardware type, where there is a CPU limit, memory limit, disk limit, or internet speed. The root cause of a problem is hardware. Solution is to do hardware optimizations like adding more CPU, more memory, or even more servers. For example, it could be a web server, or it could be a backend, a front-end server, a backend server, and a database server. What is a performance test environment? It is a dedicated setup created for a customer for load performance testing. It is separate from production staging and has a unique endpoint. You can use this testing environment to ensure the optimal performance of your systems. This is a diagram that what a performance test environment could be. So the software could be supported on an environment with dedicated servers like front end, back end, DB server, and the payment provider, for example. And this is a typical diagram of performance test environment. So it could we have in the left side we have a load generator. This is your computer. This is test engineer's computer, where the test engineer generates requests by using, for example, a tool like JMeter or a load runner or any other tool to generate requests to the test server. And the environment contains a load balancer, which balances between three web servers, and in the background there is a 1 DB server, which is correlated with each of web server. Test data for performance testing environment. Test data for performance testing environment should be the same as on production environment. The number of users and other data should be nearly the same in the performance testing environment database. An example would be that testing web pages with full DB is absolutely different than testing web pages with nearly empty DB. There are different types of environments, like quality assurance environment, QA environment, user acceptance testing environment, UAT environment, and pre-production environment. But there could be a production environment as well, but there are situations when there is a dedicated environment even for performance tests. For example, when a client invests some budget into a dedicated, separated test environment for performance, and DevOps engineers prepare this environment, and it is named like performance environment. What are the time ranges you are allowed to do a performance testing on different environments? For example, on QA, UAT, and pre-production environments, testing could be done anytime, but of course with Teams approval. Why we need this Teams approval is because engineers are working on corresponding environments, and in order to not use the same environment, so it could happen that engineers are using the same environment and performance tester is using the same environment, and it could happen that issues are occurring, and from that point of view, we need the team's approval, team lead's approval, for example, QA team lead approval, or even a manager's approval. Performance environment testing on a performance testing environment, testing could be done anytime. This is a dedicated test environment. Of course, if there are working several performance testing engineers, then you need to coordinate your time range with each of engineers. Production environment. This is testing. Testing on production environment could be done only at night. For example, when users are not using a web application. QA environment. When to perform initial testing. Yearly in the development cycle to identify and fix performance issues before the software moves to more critical environments. The ongoing testing is performed throughout the development as new features or changes are implemented. Who should approve? A QA lead oversees the testing process and ensures that performance issues are addressed, and the development team works with QA to resolve issues it identified during performance testing. UAT. When to perform pre-UAT before the software is released to end users for acceptance testing to ensure it meets performance criteria under realistic conditions. During UAT to validate that performance meets user expectations and real-world usage scenarios. Who should approve? UAT coordinator manages the UAT process and ensures performance meets user requirements, and product owner, business stakeholders approves that performance is adequate for end user needs and aligns with business requirements. Pre-production. When to perform final testing before going on live to ensure that the system performs well under production-like conditions with actual data. Load testing to simulate peak load conditions and verify that the system can handle the expected traffic and usage patterns. Who should approve? Pre-prod environment manager ensures that the environment accurately reflects production settings and that testing is thorough. Release manager approves that the system is ready for production based on performance results. Technical lead ensures that performance meets all technical and business criteria before final approval. Production environment. When to perform post-deployment. Perform monitoring and performance testing after deployment to ensure that the software performs as expected in the live environment. Ongoing. Continuous monitoring and performance tuning to address any issues that arise after the software is in use. Who should approve? Operations team monitors live performance and ensures that it meets service level agreements, SLAs. IT support engineering team handles any immediate issues and ensures that performance is within acceptable limits. Business stakeholders may review performance results to ensure that business objectives are being met. As a summary, I want to say that QA environment is used initial and ongoing performance testing approved by QA lead and development lead. UAT environment pre-release and user scenario testing approved by UAT coordinator and product owner. Pre-production environment final testing and load simulation approved by pre-production manager, release manager, and technical lead. Production environment post-deployment and continuous monitoring managed by operations and IT support with oversight from business stakeholders. Performance testing environment is very important. Each environment plays a crucial role in the performance testing's lifecycle, ensuring that the application performs optimally before it reaches end users. Let's talk a little bit about performance testing lifecycle. It is called the life cycle, or it could be called the performance testing process. The performance testing life cycle is a structured approach to evaluating and optimizing the performance of software systems. It involves several stages, each with specific goals and activities to ensure that the application performs well under expected and extreme conditions. So the performance testing life cycle happens in so-called cycles in a structured way. Performance testing life cycle contains following stages. First stage, requirements analysis, test planning, install monitoring agents on target servers, test design, test execution, monitoring and analysis, reporting, tuning and optimization, maintenance, and continuous monitoring. Requirements analysis. The objective of a requirements analysis is to understand performance requirements and goals, define key performance indicators and success criteria. Here at gathering the requirements on the requirements analysis stage, the client should define what will be the error rate, the error percentage of failed requests, and what will be the ideal response times for a page or for all the requests. For example, related to the error rate, the client could say that he wants the error rate to be not more than 5%. And related to the response times, the client could say that the response time should be no longer than 5 seconds. because if it would be longer than corresponding time, the users just will leave the site and will not continue browsing. And of course, the client should say what will be the ideal environment and what will be the resources. For example, what servers will be used, how much CPUs, how much memory, and so on. Activities during requirements analysis are gathering requirements, collect performance-related requirements from stakeholders, including response times, throughput, and scalability needs, define KPIs, key performance indicators, establish specific metrics to measure performance, such as maximum acceptable response time, transaction rate, and error rate, and identify critical scenarios, determine the critical business processes and user scenarios that need to be tested. For example, it could be defining the regression scenarios or smoke testing scenarios for performance tests. Test planning. The objective of a test planning is to create a comprehensive plan for performance testing. Define the scope, resources, and schedule for testing. Activities. Develop a test plan, outline the objective, scope, test scenarios, and resource requirements. Set up environments. Prepare the test environment to closely mimic the production environment, including hardware, software, and network configurations. Selecting tools. Choose appropriate performance testing tools and monitoring solutions. And design test strategy. Decide on the types of performance tests, for example, load, stress, scalability, soak test or endurance test, and the methodologies to be used. Of course, before proceeding to performance testing, to performance test execution, we need to install the monitoring agents on the target servers. We need to prepare all the tools for monitoring servers counters, performance counters. For example, the counters are, for example, CPU usage, memory usage, disk usage, network usage, and so on. For example, for monitoring counters on Linux server, we use the Ixora RMS tool, which is consistent from two parts. Ixora console. The Ixora console contains is the main console where all the data is coming from agents and the corresponding agents. The corresponding agents should be installed on each server. For example, we have here 3 web servers and a DB server. Ixora console, when starting the agents, all the information from agents comes to the console. Here is how Ixora RMS console looks like. And the fourth stage is to design the tests. So we need to create detailed test scenarios and scripts using a tool, for example, a load generated tool. For example, it could be a JMeter, which is widely used, and a free tool for scripting, for designing the scripts, performance testing scripts. And it could be a load runner, which is also a good tool, but it needs a license, but it is also a good tool. So the objective is to ensure that test cases are representative of real-world usage. When designing test cases, we need to take into account, for example, asking the client about what will be the delay between the steps. For example, we need to take into account the delays. For example, when user accesses one page and it needs to read, the user needs to read the content of the page, and only after that to go to the next step and accessing following pages. And this reading time should be considered into the real-world scenarios. So we need to consider this delay between the steps of a test cases. Activities of test design is to design test scenarios, develop scenarios that reflect typical and extreme user behaviors, including various load levels and transaction types. Create test scripts, write automated scripts to simulate user interactions and system load. Prepare test data, generate required data that accurately represents real-world usage patterns. And the main stage of performance testing is the test execution itself. This is the stage where the tests are executed. During test execution, we are not only executing tests, and we are not only collecting response times for requests, but we need to install the tools for performance counters monitoring. The tools for performance counters monitoring are different depending on the operating system. For example, for Windows, it is PerfMon, a tool called PerfMon, which comes incorporated together with the Windows operating system. And for Linux, it's a different tool. We could use any tool, but we used Ixora RMS tool, which is also free. The objective of test execution is to execute performance tests to gather data on system performance, simulate load, and measure system behavior. By the way, when we are executing the tests by using JMeter collects the response times automatically, so we don't need to install any tools. It collects the response times for each request. Activities during test execution contain running the tests, execute the designed performance test scenarios using the selected tools, monitor performance, track system metrics such as response times, throughput, resource utilization, and error rates during the tests, and recording data, collect performance data and logs for analysis. Then we are monitoring and analyzing. For example, the objectives would be analyze performance data to identify bottlenecks and issues, evaluate if performance criteria and KPIs are met. Activities during analysis of the performance testing results are analyzing results, review the collected data to assess system performance against the defined KPIs and success criteria, identify bottlenecks, locate performance issues such as slow response times, high resource utilization, or errors. Compare with baseline. If applicable, compare results with baseline performance metrics to identify regressions or improvements. So, for example, if we have some results of a previous performance testing execution where we are comparing current test execution with the previous test execution, and we are forming conclusions and recommendations regarding, we are comparing these two benchmarks. When it comes to the reporting stage, the objectives are communicate test findings and recommendations to stakeholders, provide actionable insights for performance improvement. Activities during the reporting are prepare test reports, document the test results, including metrics, observation, and any identified issues, provide recommendations, suggest improvements or changes to address performance bottlenecks and optimize the system, review findings, share the report with stakeholders and review findings with the development and operations team. This is a very big chapter here regarding reporting, because a report is a very important document which contains a lot of pages and a lot of information related to performance test execution. So we will have a separate chapter related to reporting later. And after that comes tuning and optimization. The objectives of tuning and optimization, it's called a performance tuning. The objectives are implement changes to enhance system performance based on test findings, verify that optimizations achieve the desired improvements. The activities are optimization of the system, make adjustments to the application configuration or infrastructure to address identified performance issues, retest, rerun performance tests to verify that the optimizations have resolved the issues and that the system meets performance criteria, and then just iterate, repeat testing and optimization as needed to achieve and maintain desired performance levels. Here on the performance tuning stage, we could optimize also the software part, but the logic of the software of the application. We could optimize the code, and we could optimize the hardware part. So the hardware relates to the environment in which the application was tested. For example, we could add more CPUs to servers. We could add more memory or a faster disks and a faster network. And there comes into play the maintenance and continuous monitoring stage. The objectives of it is to ensure ongoing performance and address issues as they arise, integrate performance testing into the development lifecycle, activities such integrate into CI/CD pipeline, incorporate performance testing into the continuous integration, continuous deployment pipeline for ongoing assessment, monitoring in production, continuously monitor the application in the production environment to detect and address performance issues proactively, update tests, revise performance tests as the application evolves, including new features or changes in user behavior. We will talk now about performance testing types. So we have a few performance testing types like stress testing, load testing, endurance soak testing, spike testing, and scalability testing. Usually, more often, only three of them are used, so stress, load, and endurance soak testing. The purpose of stress testing is to evaluate the system's behavior under extreme or beyond maximum load conditions. The objective is to identify the system's breaking point and how it fails gracefully or catastrophically when pushed beyond its capacity. The metrics collected are system stability, response time under peak load, and recovery time after failure. This is a diagram of comparison of a stress test and a load test. A stress test is increasing the number of users constantly. Every 10 minutes, it is added a specific amount of users. For example, every 10 minutes, it is added 10 more users, and so on. And then this is done in order to identify where the application crashes or the system bottleneck occurs. The load test, in comparison with stress test, is maintaining the same number of users a big period of time. For example, 50 users during a 2-hour period of time. Stress testing is done by constantly increasing the number of concurrent users for a small period of time. For example, increasing by 10 users for each 10 minutes. The test will be performed with 10, 20, 30, 40 users and so on till application will crash or bottleneck will be identified. This is a diagram of a stress testing. So we have a time and users. Every 10 minutes, so every 10 minutes, and a specific amount of users is added. For example, every 10 minutes, 10 users are added. So the test is run with 10 users, then 20 users, 30 users, and so on. For example, the application could crash or bottleneck is identified at limit of 50 concurrent users. After the limit is identified, then 2 load tests should be performed with lower limit and upper limit. One test with 40 users and another one with 60 users. Load testing. This is another type of performance testing. The purpose is to measure the system's performance under expected or typical user loads, ensures that the system can handle the expected number of concurrent users or transactions without degrading performance. So we are collecting response time, throughput, resource utilization, CPU, memory, etc. Load test is executed for a big period of time by keeping the same number of concurrent users. For example, increase the number of users slowly till 40 concurrent users, and then keeping this load for 2 hours and then stop the test. This is the diagram of load testing. So we are increasing the number of users slowly in 10 minutes. For example, from 0 to 40 concurrent users, and these 40 concurrent users are loaded in the period of time of 10 minutes. Then we are maintaining the same amount of users during a specific period, big period of time, for example, 2 hours. And when the test is stopped, we also don't stop it immediately, but we are keeping decreasing users till 0. In comparison, so load test, in comparison with stress test, a load test is not constantly increasing the number of users. It keeps the same number of concurrent users for the whole test execution. Load test should increase the number of users slowly in 10 minutes, not in 1 second. This is done in order not to stress the system under test. So another type of performance testing is endurance testing, and it is also called a soak testing. Tests the purpose is to test the system's ability and performance over an extended period under sustained load. Objective is to identify issues like memory leaks, resource depletion, or degradation over time. Metrics collected are resource utilization trends like memory CPU response time, degradation over time, and system uptime. This is the diagram of a soak testing. In comparison with a load test, where the test is executed 2 hours, the soak test should be executed much more. It should be executed 24 hours or even 2 days, and so on. And during this test, all the metrics are collected, and all the response times are collected, and error percentage are collected, and so on. And then it is the corresponding data is analyzed, and the system bottlenecks is identified, or it is identified the software bottlenecks and the hardware bottlenecks. So another type of performance testing is spike testing. Spike testing assesses the system's ability to handle sudden large spikes in user load. The object is to verify that the system can handle rapid increases in load and recover gracefully once the load decreases. The metrics collected are response time during spikes, system behavior under sudden load, and recovery speed. A spike refers to a sudden and dramatic increase in the user load or traffic on a system. This is typically an unexpected or sharp rise in demand that happens over a short period of time. Scalability testing. Scalability testing measures the system's ability to scale up or down to handle increased or decreased loads. Determines the system capacity to scale horizontally more instances or vertically, increasing resource capacity of existing instances. The collected data is performance changes related to the number of users, data volume, or other scaling factors. So in summary, we could say that often only 2 types are used: stress test and load test. Stress test is used to identify the limit of concurrent users a system can support. And then, after stress test, usually 2 load tests are run for low limit and upper limit of users. For example, if stress test identified 50 users, a load test with 40 users is run, and another test with 60 users is executed. Also, endurance soak test is run, but only if the client approves to run it, and only on performance test environment. So these three types of testing, like stress test, load test, and endurance testing, um, is included into the final report for a performance test execution. So this report is important document in which we include all the data collected and all the information related to these three types of testing. Test cases design principles. How to plan and design test cases. In the test case design stage of a performance testing process, several principles must be adhered to in order to ensure that test cases are effective, reliable, and aligned with the goals of performance testing. These principles include clear objectives, realistic workload modeling, scalability and flexibility, repeatability and consistency, resource monitoring, end-to-end performance testing, baselining and benchmarking, comprehensive coverage, automation, metrics-driven, consideration of environmental factors, risk-based testing, analysis and feedback. Clear objectives. The test cases should have well-defined objectives. These objectives should align with the key performance indicators or service level agreements that the system needs to meet. For example, defining objectives such as testing the system's response time under load or determining the system's breaking point. Realistic workload modeling. Test cases should simulate realistic user behavior and workload patterns that the system is expected to handle in production. If, for example, if 70% users perform read operations and 30% perform write operations, the test cases should reflect this distribution. Scalability and flexibility. Test cases should be designed to handle varying loads to test the system's scalability. The design should also be flexible enough to accommodate different scenarios, like increasing the number of users or simulating different environments. For example, designing tests for 100, 500, 1000, and 10,000 concurrent users. Repeatability and consistency. Test cases should be repeatable and yield consistent results across multiple executions. This allows for accurate benchmarking and comparison. For example, running the same test multiple times under similar conditions to check for consistent performance metrics. Resource monitoring. The test case design should include provisions for monitoring system resources such as CPU, memory, network, and disk I/O during the tests. For example, collecting data on CPU utilization during peak load conditions to identify bottlenecks. End-to-end performance testing. The test cases should cover end-to-end performance, ensuring that the performance of all critical components, for example, servers, databases, APIs, and the network, is evaluated. For example, testing how a request travels through the front-end, back-end, and database layer and returns a response to the user. Baselining and benchmarking. Establish a baseline by running test cases in a controlled environment to capture the current performance. Benchmark these results against design performance goals or previous runs. For example, running a benchmark test before and after system updates to assess the impact of changes. Comprehensive coverage. Ensure that the test cases cover various performance aspects, including load, stress, endurance, and spike testing. For example, creating test cases that simulate normal load testing, pushing the system to its limit, stress testing, and running for an extended period of time, endurance testing or soak testing. Automation. Where possible, performance test cases should be automated to ensure they can be executed frequently and consistently during the development lifecycle. For example, automating test cases that simulate user behavior during peak traffic periods using tools like JMeter or Load Runner. Metrics-driven. Test cases should be designed to capture key performance metrics such as response time, throughput, error rates, and latency. For example, designing test cases that measure how many transactions the system can handle per second under a defined load. Consideration of environmental factors. The environment in which the test cases are executed should mirror the production environment as closely as possible to ensure valid results. For example, replicating production-like network conditions, data sets, and server configurations. Risk-based testing. Focus on areas that pose the greatest risk to performance, such as critical paths, frequently used features, and known performance bottlenecks. For example, prioritizing test cases for high-traffic services or components that have historically shown performance issues. Analysis and feedback. Design test cases with the ability to provide meaningful feedback that can help diagnose performance issues and suggest improvements. For example, including test cases that highlight the time spent on different parts of a transaction, database query time, application server processing time, to identify bottlenecks. By following these principles during the test case design stage of performance testing, the testing process will be more robust, targeted, and effective in identifying and addressing performance-related issues. So, another very important part of test cases design principles is to take into consideration think time. So, remember, when designing test cases, take into account user think time or delays. Why this is needed? Because executing test cases without think time will result in different performance results, and comparing to test cases executed with think time, with user think time. This is an example of a scenario without a think time. So user logins, there are 7 steps. User logins to the application, go to home page, go to products page, select a product, add product to the cart, check out, and log out. And this is an example with a scenario or test case with think time. So user logins to the application, go to home page, go to products page, then the user think time, wait for 20 seconds. In these 20 seconds, users read some information, choose a product, thinks about price, and so on. So this in total 20 seconds. Then selects a product, add products to the cart, check out, and log out. Let's analyze a little bit about such a key term like latency. In order to, for example, this is a client. And we have, for example, a server. So in order to, when making a request, the request reaches the server, and then the response comes back to the client. So the latency is nothing else than just this portion, like from here to here. And this portion is just called latency. For example, a server could have its own processing time. For example, the processing time is about 10 seconds. And the request time takes 2 seconds, and the response time is also 2 seconds. When the latency equals 2 plus 2, so it is 4 seconds. Total time processing time of a request equals to 2 plus 10 plus 2, and it's 14 seconds. In other words, the latency is the time took for a request to reach the server and then to get the response back. And the processing time on the server is not took into account when dealing with latency. So the latency is only about traveling the request and response in the network. So let's talk about caching. Caching, caching is a technique used to store copies of files or data in temporary storage locations for faster access. It helps improve performance by reducing the time it takes to retrieve data and minimizing the load on backend systems. Here is an overview of caching, including its types, benefits, strategies, and considerations. What is caching? Caching involves storing frequently accessed data in a temporary storage location known as a cache, so that future requests for that data can be served more quickly. The cache can be located in various places, such as in memory, on disk, or even within a CPU. Types of caching. In-memory caching stores data in the system's memory for very fast access. Um, Examples: memcached, Redis. Use cases: session storage, frequently accessed data, computational results. Disk caching stores data on disk drives, which is slower than memory but can handle larger amounts of data. Examples: web browsers, disk-based caching systems. Use cases: large data sets, less frequently accessed data. Browser caching stores web resources like images, CSS, JavaScript on the user's device. Examples: HTTP caching headers. Use cases is to speeding up web page load times, reducing server load. Proxy caching caches responses from a server at an intermediary server or proxy. Examples: content delivery networks, reverse proxies. Uh, Use cases are distributing content geographically, reducing latency. Application caching stores data generated or used by applications to reduce repeated computations or data retrieval. Examples: local cache in web applications, data caching in APIs. Use cases: API response caching, database query results. Benefits of caching: improved performance, reduces data retrieval time and speeds up response times, reduced load, decreases the number of requests to the backend server, which can reduce server load at costs, enhanced user experience, provides faster access to frequently used data, leading to a smoother user experience. Cost efficiency reduces bandwidth and computational costs by serving cached content instead of repeatedly generating or fetching it. Caching strategies. Cache aside lazy loading, the application code is responsible for loading data into the cache when it is needed. The cache is updated only when data is read or written. Pros: easy to implement, avoids caching stale data. Cons: potentially slower on the first request as data needs to be loaded into the cache. Read-through caching. The cache automatically loads data when it is requested but not found in the cache. This strategy abstracts cache management from the application. Pros: simplifies cache management for the application, ensures data is loaded into the cache. Cons: can result in overhead and latency if not implemented efficiently. Write-through caching is when data is written to both the cache and the underlying data store simultaneously. This ensures that the cache and data store are always in sync. Write behind write-back caching. Data is written to the cache and asynchronously written to the underlying data store. This can improve write performance, but may introduce risks of data loss if the cache fails. Cache invalidation. Cache invalidation is the process of removing or updating cache data when it becomes stale or outdated. Common strategies include time-based expiration, event-based invalidation, and manual invalidation. Time-based expiration stands for cache data is invalidated after a certain period of time. For example, using time to live. Event-based invalidation data is invalidated based on specific events or triggers. For example, when updates to the underlying data store. Manual invalidation cache entries are manually removed or updated by administrators or application logic. Considerations for implementing caching. Consistency. Ensure that cache data remains consistent with the source of truth. Size and capacity. Manage the size and capacity of the cache to avoid excessive memory or disk usage. Security. Consider the security implications of caching sensitive or personal data. Performance impact. Measure and monitor the impact of caching on application performance to ensure it meets desired goals. Caching is a powerful technique for improving system performance and efficiency, but it requires careful planning and management to balance speed, consistency, and resource utilization. So let's discuss on HTTP connection or Hypertext Transfer Protocol. HTTP is a fundamental protocol used for transmitting data over the web. It forms the foundation of data communication on the World Wide Web and is used for requesting and delivering web pages, images, videos, and other resources between clients and servers. So HTTP is an application layer protocol in the OCI model. It operates on top of the transmission control protocol and uses port 80 by default. HTTP versions. There is a version 09. This is the first version of HTTP introduced in 1991. Was very basic and only supported the GET method to request raw data. HTTP 1.0 introduced in 1996. It added support for headers, status codes, and additional methods like post and head. HTTP 1.1 released in 1999. This version introduced several enhancements, including persistent connections, chunk transfer encoding, and additional methods. HTTP 2, published in 2015. HTTP 2 improved performance and efficiency with features such as multiplexing, header compression, and stream prioritization. And HTTP version 3, the latest version, based on quick UDP internet connections, aims to further improve performance and security by using UDP instead of TCP. HTTP methods. HTTP methods define the type of action to be performed on specified resource. Common methods include GET, requests a representation of the specified resource. It is a safe and idempotent method. POST submits data to be processed by the server, often resulting in a change in the server state or side effects. PUT updates or creates a resource at the specified URL. Delete removes the specified resource. Head, similar to GET but only retrieves headers and not the body. Options describes the communication options available for the target resource. Patch applies partial modifications to a resource. HTTP headers provide metadata about the request or response. They can be classified into request headers, provide information about the client's request. For example, user agent identifies the client making the request, for example, the browser type. Accept specifies the media types that are acceptable for the response. Authorization contains credentials for authentication. Response headers provide information about server's response. For example, content type, which describes the type of the content being sent. Content length indicates the size of the response body in bytes. Location used in redirections to specify the new URL. HTTP status codes. Status codes indicate the outcome of HTTP request. They are categorized into 100, for example, indicates that the request has been received and is being processed. For example, 100 continue, the initial part of the request has been received and the client can continue. 200 indicates that the request was successfully processed. For example, 200, it's okay, the request was successful and the server returned the requested resource. And 201 created, the request was successful and a new resource was created. Redirection indicates that further action is needed to complete the request. For example, 301 moved permanently. The requested resource has been permanently moved to a new URL. 302 found the requested resource resides temporarily under a different URL. And client error indicates that the request contains bad syntax or cannot be fulfilled. For example, 400 bad request, the server could not understand the request due to invalid syntax. 404 not found, the requested resource could not be found. The server errors indicates that the server failed to fulfill valid request. 500 internal server error, the server encountered an unexpected condition. 502 bad gateway, the server received an invalid response from the upstream server. HTTP is a vital protocol for web communication, providing a foundation for data exchange between clients and servers. Understanding its versions, methods, headers, status codes, and security aspects is crucial for developing and maintaining effective and secure web applications. Hello, today we will discuss about a case study. Case study is a detailed examination of a specific instance or example used to explore more complex issues, understand processes, and derive insights that can inform practice or theory. A purpose of a case study is, first of all, it is exploration of complex issues. Case studies help in understanding intricate problems or phenomena that cannot be easily analyzed through other research methods. In-depth analysis. They provide a comprehensive view of the subject by examining multiple aspects and factors in detail. Real-world applications. Case studies offer practical examples and real-world scenarios that can be used to illustrate theoretical concepts or inform decision-making. Today, we will analyze 4 case studies in the performance testing domain, and every case study includes background, objective, performance testing approach, results, and conclusion. A first case study is related to e-commerce website load testing. An online retail company was preparing for its annual sale event, which typically attracts a massive influx of customers. The website has a history of crashing during high traffic periods, and the company wanted to ensure that it could handle the anticipated load this time without any issues. Objective: to test the website's performance under peak load conditions, simulate the expected traffic during the sale event, and identify any bottlenecks or points of failure. Performance testing approach. First of all, it is a load testing. Simulate a user load of 100,000 concurrent users to mimic the anticipated traffic during the sale event. Use tools like Apache JMeter or Load Runner to create virtual users that replicate the behavior of real customers: browsing, searching, adding to cart, checkout. Measure response times, throughput, error rates, and server resource utilization. Another performance testing approach would be stress testing. Gradually increase the number of concurrent users beyond the expected peak, for example, up to 200,000 users, to determine the website's breaking point. Identify how a system behaves under extreme conditions and if it fails gracefully, providing proper error messages and maintaining partial functionality. The third performance testing approach is scalability testing. Assess how well the system scales with increasing loads by adding more servers or resources, vertical and horizontal scaling. Ensure that performance improves proportionally with added resources. Endurance testing, or soak testing. Run the load test over an extended period, for example 48 hours, to identify memory leaks, slow database queries, or any degradation in performance over time. So as a result of executing performance tests, we have some bottleneck identified. The load test revealed a bottleneck in the database layer due to inefficient queries and limited connection pooling. Mitigation: optimized the SQL queries, implemented better indexing strategies, and increased the database connection pool size. Outcome: after optimization, the website successfully handled 150 concurrent users with an average response time of 2 seconds, significantly below the 3-second target. As a conclusion, the company's website was able to handle the anticipated load during the sale event without any major outages or performance degradation, resulting in a 20% increase in sales compared to the previous year. And here we have case study number 2 about mobile banking application. And it is about testing the response times. As a background, the leading bank developed a new mobile banking app to offer customers better features and a more user-friendly interface. However, during beta testing, customers reported slow response times when accessing certain features such as viewing a transaction history or transferring funds. Objective is to measure and optimize the response times of the mobile app's key functionalities under normal and peak user loads. Performance testing approach. Baseline performance testing. Conduct baseline tests with 100, 500, and 1000 users to measure response times for key actions. Login, view transaction history, fund transfer. Use tools like JMeter and Appium to automate mobile interactions and simulate real-world usage patterns. Spike testing. Simulate sudden spikes in user load. For example, 10,000 users logging in within a minute to see how the app responds to traffic surges. Monitor the app's ability to handle rapid increases in traffic without crashes or unacceptable response delays. Network condition testing. Test app performance under different network conditions, 3G, 4G, 5G, and Wi-Fi using network link conditioner. Identify any network-related performance issues, for example, slow loading times over 3G. After performance tests execute, we have following results. Issue identified. Slow response times were traced to the app's backend server, which was not optimized for handling high volumes of simultaneous requests, particularly during fund transfers. Mitigation. The development team optimized the service handling of concurrent requests and added caching for frequently accessed data like transaction history. Outcome. Post-optimization, the response times improved by 60% with a consistent performance across different network conditions. In conclusion, the company successfully improved its app's performance, resulting in positive user feedback and a 30% increase in daily active users within the first month of the app's official release. Case study 3. It is about video streaming platform throughput testing. A new video streaming platform aimed to compete with established platforms by providing high-definition video streaming services. The company needed to ensure that its servers could handle a large number of concurrent users streaming HD and 4K videos without buffering or quality degradation. The objective is to test the throughput capacity and quality of service of a platform when streaming HD and 4K content under different network conditions and varying loads. Approach: throughput testing. Simulate multiple users streaming HD and 4K videos concurrently using tools like Gatling and Artillery. Measure the maximum data throughput in megabytes per second that the platform's network infrastructure could handle without video buffering or quality drops. Buffering and playback testing. Analyze the video buffering, startup time, and bitrate switching under varying network conditions. Slow networks, high packet loss, and so on, using Wireshark and Charles Proxy. Test video playback with different buffer sizes and adaptive bitrate settings to optimize the end-user experience. Capacity planning and scalability. Evaluate the scalability of a platform by adding more edge service and content delivery network nodes. Simulate global user distribution to test server and CDN performance under a geographically dispersed load. As a result, we have issue identified. Initial testing showed significant buffering and video quality degradation when more than 5,000 users streamed 4K videos simultaneously. Mitigation: improved CDN configurations, implemented dynamic bitrate adjustment algorithms, and optimized video encoding settings to reduce file sizes without compromising quality. Outcome: after optimizations, the platform handled 20,000 concurrent users streaming 4K content with minimal buffering and smooth playback. In conclusion, the company achieved its goal of providing a seamless streaming experience, leading to a 15% increase in subscriptions and the first quarter post-launch. Case study 4. Cloud-based SaaS application performance testing. A cloud-based SaaS company provides data analytics services to multiple enterprise clients. The company experienced slow query performance and data processing delays during peak hours, affecting client satisfaction. The objective is to identify and resolve performance bottlenecks in the application, particularly during peak usage times, and ensure consistent service delivery across different regions. Performance testing approach. First of all, we make a stress test. Perform stress tests by simulating peak loads, 5 times more than the average user count, using NeoLoad and JMeter to determine how the application behaves under extreme conditions. Measure query response times, application throughput, and error rates. Database performance testing. Focus on testing database query performance, indexing strategies, and caching mechanisms. Use tools like SQL Profiler and Dynatrace to analyze low-performing queries and database locking issues. Geolocation testing. Simulate user traffic from different geographical locations to test performance consistency across multiple regions. Use cloud-based load testing tools like Leader.io and Redline 13. After performance tests execute, we have identified issues. The application experienced web performance degradation due to inefficient SQL queries and lack of proper database indexing. As a mitigation, the database was restructured with optimized indexing, query optimization, and improved caching strategies. As an outcome, the average query response time decreased by 40%, and the application maintain consistent performance even under peak loads. In conclusion, a Data Pro company achieved a 25% increase in client retention rates due to improved application performance, enhancing its competitive position in the market. These case studies illustrate how different performance testing strategies can be applied to various applications, from e-commerce websites to cloud-based SaaS platforms, to identify bottlenecks, optimize performance, and ensure a positive user experience. So let's talk about testing mobile applications with JMeter. Here's a step-by-step guide on how to use JMeter to test mobile applications. First of all, we need to understand the mobile app's architecture, and we need to identify API endpoints, determine which APIs your app is using to communicate with the backend. This may include endpoints for user authentication, data fetching, form submissions, and so on. Request types. Understand the types of HTTP requests used, for example, GET, POST, PUT, DELETE, and so on. Parameters and headers. We need to identify parameters, headers, cookies, and authentication tokens required by each request. We need to have a JMeter installed on our system. We need to configure JMeter for mobile app testing. To test the backend APIs used by the mobile app, we need to configure JMeter as a proxy server to capture the HTTP requests sent by the app. So we need to add a thread group. We need to set up JMeter as a proxy server. We need to configure the mobile device to use JMeter as a proxy. And we need to install JMeter CA certificate on the mobile application. For adding a thread group, you just need to add it to the test plan level. Just right click on test plan, add threads, thread group, configure the number of users, ramp up period, and loop count to define the load simulation. When setting up JMeter as a proxy server, just right click on the thread group, add a logic controller and a recording controller. Right click on workbench or test plan. In newer versions, just click add non-test elements, HTTPS test script recorder. Then you need to configure the port, for example 9090. The JMeter will use to act as a proxy, and click start to start the JMeter proxy. When configuring your mobile device to use JMeter as a proxy, you need to connect your mobile device to the same Wi-Fi network as your computer. Go to network settings on your mobile device and configure the Wi-Fi proxy to point to your computer's IP address and the port number JMeter is listening on, for example 9090. And after that, we need to install JMeter's certificate. To capture HTTPS traffic, you need to install JMeter's certificate on your mobile device. The certificate can be found in JMeter's bin directory, usually named Apache JMeter Temporary Root CA certificate. Transfer the certificate to your mobile device and install it. Follow the device's instructions to install a custom CA certificate. The fourth step is to record the mobile application traffic. So we need to start recording with JMeter. Just open mobile application and start performing some actions we want to test. For example, logging in, browsing, performing searches. JMeter will capture the HTTP requests and record them under the recording controller. And after that, we just need to stop recording. Once we have captured the necessary requests, click stop in the JMeter's test script recorder. The fifth step is to customize and enhance the recorded test plan. So we need to organize and rename requests. We need to add dynamic parameters, add assertions, add timers, and add listeners. Organize and rename requests. Review the recorded requests in the recording controller. Organize them logically and rename them for the better readability. Add dynamic parameters. Some requests may require dynamic parameters, for example, session IDs, authentication tokens. We need to use JMeter's post processors like regular expression extractor or JSON extractor to capture these values from previous responses and inject them into subsequent requests. When adding assertions, to add assertions, just right-click on request, add assertions, response assertion, define assertions to validate response data, such as checking for a specific response code, for example, 200 for OK response code, or verifying that a particular text appears in the response body. After that, we need to add timers. Add timers to simulate real user behavior and delay between requests. Just right-click on request, add timers, constant timer or a Gaussian random timer, and so on. After that, we need to add listeners. Just click on thread group, add listener, and choose the listener you like. For example, view results tree for capturing errors, or summary report, or graph results, or aggregate report, and so on, to capture and visualize the test results. After that, the next step is to configure the load test parameters. We need to set the number of threads, the number of concurrent users, and we need to configure other test parameters. When in thread group, for setting the number of threads, just in the thread group settings, specify the number of users, number of threads, the runtime time, and loop count to define how the load will be generated. For example, 100 users with a 10-second ramp-up period, but for 100, 10 seconds will be too short period of time. I would recommend, for example, 5 minutes or 10 minutes and so on. And but we can configure 100 users with a 10-second ramp-up period, which will start 10 users per second. And configure other parameters like ramp-up period, the time JMeter takes to start the total number of threads, loop count, the number of times to execute the test plan for each user. And after that, we run the performance test. So we save the test plan and we run the test. When running the test, we need to analyze the test. After running the test, we need to analyze the test results. We need to check errors. We need to check response times. Also, we need to identify any bottlenecks. We need to analyze the performance testing counters and identify any bottlenecks. And we need to export the results. After that, we need to optimize and retest. So we need to optimize the backend services, and we need to rerun the tests. Based on the results, just optimize the backend, the server, for example, adding some more resources or the database or APIs to address the identified issues. After optimizations, we need to rerun tests after applying optimizations to validate the improvements and ensure no new issues have been introduced. Also keep in mind that we need to take into account the continuous testing and monitoring. We need to incorporate the JMeter tests into a CI/CD pipeline, and we need to monitor the performance test results in production. Integrate JMeter tests into the CI/CD pipeline to automatically run performance tests whenever there are changes to the backend or mobile app, and use real user monitoring tools alongside synthetic tests to continuously monitor the app's performance in production. Also, we have some best practices for mobile app testing. Simulate realistic scenarios, parameterize tests, optimize thread counts, monitor resource utilization, and use real devices for accuracy. Test scenarios should closely mimic real-world usage patterns, including different user actions, network conditions, and devices. When parameterizing tests, we need to use dynamic variables for data that changes, like user credentials or session tokens, to avoid hard coding. On optimizing thread counts, we need to start with a small number of threads and gradually increase to avoid overloading the test machine. On monitor resource utilization, while running tests, we need to monitor the resources like CPU, memory of a server and client machine to ensure they are not bottleneck. And we need to use real devices for accuracy. We need to test using real devices or cloud-based device farm to get accurate results, as emulators may not reflect the real-world performance. By following these steps and best practices, you can effectively use JMeter to test the performance of mobile applications and ensure they meet the required performance standards under various conditions. So let's talk about JMeter reports. We have two types of reports. We have real-time reporting, like listeners, and we have JMeter dashboard report, which is an HTML report. When speaking about real-time reporting about listeners, we have following types. We have view results tree, we have view results tree in table, aggregate report, graph results, and summary report. Some of these reports you already know, and we will talk about HTML report. The key features of HTML report are response time percentiles, error statistics, throughput and latency graphs, response time over time, and request and response metrics. So I have prepared the following project for testing the report generation. So we have 4 steps. Step 1, login, open product list, open product details, and logout. And these requests are pointing to blazedemo.com, and I have used some timers. For example, the think time for opening product list is 2 seconds. The think time of opening product details is 3 seconds, and the user should read the product details about 4 seconds, and after this the occurs logout step. And I have added the view results tree in order to check this test script if everything runs smoothly. I will run it with one single user. So let's run it. Everything is fine. So I'm clearing results, and I will set number of threads to be, for example, in order just to test the report generation, I will use one thread, and will loop count will be 20, for example. I'm saving the report. After this, I need to open in order to generate the output file. I will need to use some commands. So the commands are as follow. So if you see, I have prepared following commands. The first command is for running JMeter test script and generating a log file with all the requests and all the information related to errors. And for this, I'm just using JMeter -n -t test plan and -l and test result GTL. And after this, we need to generate the report. And the command for generating the report is JMeter -g. I'm giving as input the log file, and based on this log file, the report is generated in the output folder. So let's run the test plan first. So I will need to just right click on JMeter bin folder and okay, let's open the command line. Then type F cd. So now I am in the bin folder, and in the bin folder I need to, okay, the test plan is saved, and I will need to go to the test plan folder, test plans. So I will need to use the command. Okay, so the command is prepared. So JMeter, I'm giving the test plan, then I'm giving the log file. So let's test this. Okay. Okay, so everything is fine, so let's just run it. Okay, so the test was run, and now we need just to check the output file. So we have in test plans in logs, and here we have a output file, the log file, which is named report generation test result.gtl. Okay, and we will use this file in order to generate the report. So let's prepare the command. So I'm just I need to point to the right folder. So this one. Okay, and after providing the log file, I need to provide the output folder for the report to be generated. So I will just let's so I will provide this folder. After preparing the command in Notepad, you can just copy it and okay, so let's check once again. So everything is fine. So and press enter, and we will have a report generated. Okay, the report is generated. Let's check the output folder. This is the report. So the folder, and this is the HTML report. And let's it has two folders and two files. So content, like CSS, JavaScript, and pages. And let's open it and let's check it. Okay, I have opened this file, and this is how it looks. So we have source file name, we have start time, we have end time, and this is the basic information. So we have a summary as well with the passed and failed requests. So everything, all the requests were passed. So this summary is green, and we have different charts like overtime, throughput, and response times. Let's check response times. Okay, these are the response times per request, per each request. So we have this chart, and we have response time overview. We have here where requests having response time less than 500 milliseconds, when requests having response time more than 1.5 seconds, and when more than 500 milliseconds and less than 1.5 seconds, and the request in error. Time vs threads chart. We have also response time distribution. Let's check the overtime, response times over time. So we have active threads over time. So only one thread. Response time percentiles over time. Successful responses. Okay. Bytes throughput over time. Then latencies. Then we have connect time over time. Okay, and also we have throughput, transactions per second, and so on. Okay, this is one report, and let's check what will be the result if we will run, for example, 50 users, 50 concurrent users. First of all, we need to change here to be 50 concurrent users, and ramp up period in seconds will be 1 minute. Let's save it, and let's use following command. The second log file. Okay. So as you can see, we have some intermediate results, and in the first intermediate result, we have active 7 threads. Average time is 1 second. Okay, we have 32 threads. And now all 50 threads are loaded into the system, so they are working now in parallel. So we have 50 concurrent users working at the moment. Okay, the test is run successfully, and let's check the file. Let's check the log file. So the second log file is much more greater than the first one because it contains much more results. So if you want, you just need to open. For example, let's open this one, and as you see, it contains the information related to all of the requests, their status, their time, average response time, and so on, and the name of request. Okay, let's use this log file in order to generate the report. Let's prepare the command. So, okay, just running the command. It should create the folder. It created the folder, and this is the report, and you can just open it. So let's see. Let's see, for example, the active threads over time. As you can see, there are not one thread, but there are 50 concurrent threads which have worked in parallel. And also you can see the statistics on the dashboard of this report. We have for each request we have statistics and the number of samples. So we have average time for each request. We have minimum and maximum time, and also we have error percents. So as you can see, the error percent is 0 for all the requests. So everything was fine. And I just wanted to mention that instead of using a simple thread group, you could probably use some other type of thread group which will ramp up all the threads and then will constantly keep these threads working in parallel, for example, constantly, for example, for 2 hours. And after 2 hours, it can just decrease the number of threads slowly in order to not stress the system. Also, when ramping up, you need as much for example, if you have 1,000 users, then you need to increase the ramp-up period of time in order to not to stress the system.